Welcome to lecture 9 of the wireless communication course. Today we will talk about multi-user communication. So today we will learn about the difference between uplink and downlink. We will learn about multiple access and random access. We'll also see mathematical models for different multiple access schemes and also the notions of signal to noise ratio, signal to interference ratio, and signal to interference plus noise ratio. The topics for today, they are covered in these parts of the textbook, so please have a look in these sections. Last time we learned about OFDM, where we saw that in order to increase the data rate, we need to increase the bandwidth, and then there's an elegant digital implementation based on fast Fourier transform and the cyclic prefix, where in the time domain we take our samples and we copy the last part and put it in the beginning so that the receiver thinks we have a periodic transmission. The cyclic prefix should be longer than the delay spread of the channel, and the OFDM symbol duration should be less than the coherence time of the channel. Under these conditions, we create a circulant channel, which then translates to multiple parallel data streams. Since we have such parallel data streams, we can combine with water filling. This was the transmit structure, so we take our QAM data in the frequency domain, convert to time domain with an FFT, insert the cyclic prefix and send over the channel. At the receiver side, we downconvert, filter and sample, then we have samples in the time domain. We remove the cyclic prefix, this requires of course some synchronization. Then take an FFT to convert back to the frequency domain, and then in this frequency domain our observations are just the transmitted symbols times the channel plus noise. So we can then perform subcarrier by subcarrier maximum likelihood detection. Today's topic will be multi-user communication. In multi-user communication, there are two main schemes. The first one is the cellular scheme, the other one is the ad hoc scheme. So we will mainly talk about cellular. In here we have a base station and multiple mobile users, and then we divide up the communication from base station to users as downlink. This is shown here. So there's a base station communicating with different users, sending signal to each user. The signal goes through a channel which depends on the user, and then noise is added at the user side. So different users have different channel and different noise, and each user has its own observation, and then should recover the data intended for that user. The communication from the users to the base station is called uplink. Again, each user will now send its own signal going over its own channel. These signals are then added together at the base station side with noise, and then the goal of the base station is to recover the signals from each of the users. Now, it will turn out to be mathematically convenient to think of the following single channel user communication, so the single user communication, where we have a transmitted signal of this form. So the transmitted signal for a certain user is a superposition of pulses. So AL here represents the data symbols, and S of t represents the pulse shape, TS is the pulse duration. And we can mathematically write this in a very equivalent way as just SL of t. So you can interpret that the signal that is sent is a superposition of data symbols. Each symbol has its own pulse, and these pulses here happen to be time shifted. Later we will generalize this. The receiver then sees this received waveform. What the receiver then does for optimal processing is it would apply a matched filter. So to recover the alt symbol, it will apply a filter matched to the alt transmitted symbol, its transmitted pulse. And then it has this kind of observation. So you have superposition of all transmitted pulses, a correlation between the alt pulse and the alt primed pulse, and then the noise. And when these signals are orthogonal, which you would have if your transmit pulses are square with Nyquist pulses, then this becomes a Nyquist pulse. Then this correlation goes to 0, and then we recover exactly our alt symbol plus noise. So again, we are using different signals for each transmitted symbol, and these signals can be designed to be orthogonal, which is what we typically do in the single user communication. And today we will generalize this to multi-user. A first concept introduced is so-called duplexing. Duplexing refers to the separation between uplink and downlink communication. These cannot happen in the same time frequency band because then they would interfere with each other. There are two common duplexing schemes. One is frequency division duplexing. So here the base station will be allocated a certain band for downlink communication and a certain band for uplink communication. And this means that these can happen at the same time, and the base station would transmit over one band and at the same time listen on another band. In between there will be a guard band to avoid leakage from uplink to downlink. Another scheme, which of course is related to the frequency domain, is then the time domain or time division duplexing, where the base station switches from downlink and uplink communication at different times. So for some time it will do downlink communication over the entire frequency band. Then there's a small guard time, and then the base station will switch to uplink communication. They have different benefits and drawbacks, of course. So in time division duplexing, there can be some delay because you need to wait to do your transmission. It also requires tighter synchronization. It is better for asymmetric traffic because you can choose to have more downlink slots than uplink slots. And very important for later lectures is that you can exploit the channel symmetry. This means that when from the base station, let's say this is a base station and this is a user, there's a certain channel from the base station to that user. From the user to that base station, the channel will just be the transpose. In case we have multiple antennas. And this is the symmetry of the uplink and downlink channel. When you use, this is for time division duplexing, when you use frequency division duplexing, the channel from the base station to the user will be again H, but the channel from the user to the base station will now be a different channel G because it's on a different frequency band. So this means that even if the base station knows the uplink channel, it doesn't have any information about the downlink channel. On the other hand, with time division duplexing, if the base station knows the uplink channel, it knows then the downlink channel. It's just a transposed. And this can then be exploited for communication purposes. And this will be a major topic in 5G communication. Now, given a certain duplexing scheme, for instance, frequency division duplexing, we then need to also decide how to do multiple access. This means how we separate users within the given duplexing scheme. And we do this by creating dedicated channels for the different users. So multiple access can be combined, with FDD or TDD. And the multiple accessing schemes are FDMA, TDMA, and CDMA. So you can have FDD plus TDMA, you can have TDD plus TDMA, and any possible combination you can think of. Now, the name already tells a lot about these schemes. So in FDMA, different users will just have different frequency bands. In TDMA, different users will have different time slots. And in CDMA, different users will have different codes. And we will see in more detail how this works. But I think FDMA and TDMA are relatively obvious. So you just give each user its own very small frequency band. And by separating these bands, you will make sure that the users don't interfere. In TDMA, you give different users different time slots. So each user is only allowed to transmit or receive for a certain amount of the time. And by making sure these time slots are not overlapping, you again create orthogonal transmissions. The nice thing now is that we can reuse the previous mathematical model to capture all of these multiple access schemes. And the idea is that each user has its own waveform, and each user then for each transmitted symbol has also its own waveform. So this is how we denote this. We will say this is the signal for user K and for symbol L. And then, of course, the second term here is the signal for user K prime and symbol L prime. And we will now design these waveforms to be mutually orthogonal. So this means that these signals are, this correlation here is 0 when we have two different users, or when we have two different times, even if it's for the same user. And the correlation will only be non-zero when we're looking at the same time and the same user. And that means that the signal associated with user k is given by this expression. Okay, so xkt is the signal for user k, uplink or downlink. It's given by a superposition of symbols. AKL is the alt symbol for user k. SKL is the pulse that is used for the alt symbol of user k. So then in TDMA, this is what it looks like. So user 1 will have some pulses at some time. So this means, for instance, that S1 1t, we will have S1 2t, S1 3t. Let's say that the user is just sending 3 pulses. Then the user will occupy 3 symbol slots. One for S1 of t, S2 of t, and S3 of t. And then the user has to wait. And then again, later the user gets 3 slots. And in between, other users can transmit. And by doing this, when you then compute the correlation of S11t with, for instance, S21t, dt with a complex conjugate. So let's say that user 2 is sending a pulse here. This correlation will be 0 because the pulses do not overlap in time. A similar story happens in the frequency domain. So here users are allocated different frequency bands. And because these bands are orthogonal, so they don't overlap, this correlation will be 0 when you have 2 different users. So again, the point is that each user will get its own set of waveforms, and these waveforms are mutually orthogonal. So the different users, they don't see each other. Different symbols from the same user don't see each other, and you only have signal when you are looking at the correct user and the correct time slot. Good, I will skip this example and move forward to the next topic, which is then CDMA. So CDMA along with TDMA and FDMA is a more complicated multiple access scheme, which we then again try to design as follows. So we have again orthogonal waveforms for different users and different times. And we've seen 2 special cases, TDMA and FDMA, but this constraint is much more general and you can design other signals that allowed for this constraint. In CDMA, what we do is we give each user dedicated codes. So this is an example here where we have 3 users and user 1 has this code. So this means that for user 1, we have signal S1L of t will be given by this signal. So you just send a sequence of pulses like this. And then user, well, let me make it a bit more specific. User 1, 1, user 1, 2 of t will be first nothing, and again, the same sequence of pulses. And now this time here is the symbol time. So that means when we're sending our second symbol, for the second case here, when we're sending our second symbol, we use 4 of these pulses. So this implies that the symbol duration will be greater than the pulse duration. Or this also means that TS will be much greater than 1 over the bandwidth, right? Because these pulses are very short, they will have a larger bandwidth, so then this will hold. Now, how do we make sure that this constraint is satisfied? We do this by correlating these pulses. So here are some examples. Show that user 1 and user 2 are orthogonal. I don't think I derive it explicitly. User 1 and user 2 are orthogonal. You can see this easily. So let's suppose that user 1 is sending 1, 1, 1. User 2, 1, minus 1, 1, minus 1. Then we compute this correlation. And now you can do this correlation directly in digital. So we have 1 times 1 plus 1 times minus 1 plus 1 times 1 plus 1 times minus 1. And this is equal to 0. So user 1 and user 2 are orthogonal. User 2 and user 3 are not orthogonal. Okay, and again, you can see this. So user 3, I have -1, 1, -1, 1. And then this cross correlation will be 1 times -1 plus 1 times -1 plus -1 times 1 plus 1 times -1. So this will be -4. So these users are very correlated, which means that this does not hold, which means that they will interfere with each other. Good. So now that we understand these different waveforms, TDMA, FDMA, and CDMA, and they all have the same structure, we can now look at how they perform in uplink and downlink.